Okay, let's just dive right in, shall we? Today, we are looking at an absolute legend, both mechanically and culturally, the V8 engine. Whether you're a seasoned gearhead or just someone who appreciates that visceral, ground-shaking sound of a classic muscle car, you know the V8 holds a totally unique place in automotive history. In this explainer, we're going to unpack exactly what makes this engine tick, going all the way from the basic physics of combustion down to the actual engineering secrets behind that legendary sound.
Actually, there's a quote from our sources that really just hits the nail on the head. The passion towards the V8 design ensures that it will endure. I mean, we all intuitively know and respect the V8's raw power, right? It's an engine that's pushed its way into massive luxury saloons, nimble sports cars, off-road beasts, power boats, and believe it or not, even aircraft. It's a design literally driven by passion, which is the perfect setup for our journey today to uncover exactly how this incredibly enduring machine actually works.
So, here's the schematic for today. We'll start off with the anatomy of a V8, move right into the four-stroke cycle, examine the different valve trains, uncover the secret V8 rumble, and finally, look at the engine's lifeblood.
All right, Section 1, Anatomy of a V8, the iconic V layout.
You know, the V8 gets its name in a wonderfully literal way. It's built around a cylinder block shaped just like the letter V, usually sitting at a 90-degree angle, and it contains exactly 8 cylinders. But to really appreciate this beast, we kind of need to rewind the clock to ground ourselves in its history. The foundational technology here, the Otto cycle, was invented way back in 1876. Think about that for a second. That's decades before true automobiles were even roaming the streets. Fast forward a bit, the very first V8 engine rolled out in 1914. But it wasn't until 1932, when Ford introduced the famous flathead V8, that the engine really exploded in popularity and became accessible to the everyday driver. It's been a steady, fascinating evolution ever since.
It all goes back to Nikolaus Otto's very first four-stroke engine. And honestly, this is the crazy part to me. Despite all the computer chips, the insanely precise machining, and the advanced materials we have today, the mighty modern V8 still relies entirely on this fundamental 1876 four-stroke Otto cycle. Let's dig into that and see how it builds the core heartbeat of the engine.
Which brings us to Section 2, the four-stroke cycle, intake to exhaust.
Let's slow things down a second and look inside just one single cylinder. There's a precise four-step dance happening here that literally turns air and fuel into raw mechanical force. Step 1 is intake. The piston drops downward, pulling in a fresh mixture of air and fuel. Step 2 is compression. The piston shoots back upward, tightly squeezing that mixture together. Then, Step 3 is power. A spark plug fires, instantly igniting the compressed gas and violently forcing the piston back down at blinding speed. Finally, Step 4 is exhaust. The piston comes back up one last time, clearing out the spent gases, so the whole cycle can happen all over again.
So, the real magic is how this cycle translates across 8 separate cylinders to create the V8's legendary smoothness. In a V8, you have a cylinder firing for every 90 degrees of crankshaft rotation. 90 degrees. That number is absolutely crucial. It means that at literally any given millisecond, there are 2 cylinders simultaneously on a power stroke. If you contrast that with your standard 4-cylinder engine, which only has 1 cylinder firing at a time, it instantly makes sense why the V8 delivers its power so incredibly smoothly.
All right, Section 3, Valve Trains, Pushrod versus OHC.
I like to think of it this way. If the cylinders are the stomach digesting the fuel, the valve train is the engine's lungs. It's the entire biological system deciding how the engine breathes air in and pushes exhaust out. And in the engineering world, there's a pretty intense rivalry between the 2 main designs here. On one side of the ring, you've got the pushrod, or overhead valve design. This is your classic old-school muscle. Because the camshaft is tucked deep down inside the engine block, the overall package is remarkably compact. It's incredibly simple, practically bulletproof, and it churns out massive low-end torque. On the flip side, you have the overhead cam, or OHC engine. By moving the camshafts all the way up to the top of the cylinder head, you completely ditch those heavy pushrods. This allows the engine to rev much higher and breathe way better through multi-valve setups. But of course, a trade-off. It comes at the cost of being larger, heavier, and significantly more complex to build.
A great example of this high-revving tech in action is the classic Rover V8. Our sources highlight this specific engine because it holds a really cool piece of history. It was the very first V8 engine to use this overhead cam system. They actually took an older pushrod design they bought from Buick, engineered it over to overhead cams, and put it into production in 1965.
completely unlocking that higher speed and efficiency.
Section 4. The secret V8 rumble. It's all in the crankshaft.
Down at the very bottom of the engine block lives the crankshaft. This massive, spinning piece of heavy metal is where the engine finds its physical balance. But more importantly, it's where it gets its iconic voice. There are basically two totally different ways to design a V8 crankshaft. First up is the crossplane crank. Here, the connection points are offset by 90 degrees. Now this design requires large, heavy counterweights to balance out the rocking motion of all those pistons. Because of all that extra weight, it doesn't rev super high, but that exact 90-degree firing sequence, that is exactly what produces that classic, deep, woolly rumble we all associate with American muscle cars. Then, on the other hand, you have the flat plane crank, where the pistons are simply offset by 180 degrees. It's way lighter, which means it revs incredibly fast, but it changes the sound profile entirely. It makes the engine scream, almost like two inline-four engines strapped together. If you're thinking high-end European supercars, you're thinking flat plane crank.
And finally, Section 5, the engine's lifeblood, lubrication systems. We are into the final, yet arguably the most vital, subsystem of the whole machine. If the valve train is the lungs, the lubrication system is the beating heart, and the oil itself is the literal lifeblood. Think about it. A V8 has thousands of violent metal-on-metal explosions happening every single minute. Without oil, those high-speed metal parts would literally melt down from friction in a matter of seconds. This survival system relies on three key components working in perfect harmony. The oil pan sits right at the bottom, acting as a massive reservoir. Then you have the oil pump, that beating heart, which sucks oil from the pan and aggressively shoves it through the engine's tiny passageways under intense pressure. Finally, the oil filter steps in to catch any highly abrasive metal shavings and dirt. Together, these three create a microscopic film of oil that keeps the moving metals completely separated. It stops friction dead in its tracks and regulates extreme engine temperatures by absorbing and whisking away heat.
To really grasp how crucial this is in the real world, we need to demystify a word you've definitely seen on the shelf at the auto parts store: viscosity. Viscosity is simply an oil's resistance to flow. This right here is where cold, hard engineering meets your everyday car maintenance. A low-viscosity oil flows really fast, which is absolutely critical for instantly coating your engine parts when you start your car on a freezing winter morning. A high-viscosity oil, however, is thicker, meaning it maintains its protective barrier even under blistering temperatures and heavy stress. So when you grab a bottle and see a grade like 5W30, that first number is telling you how well it flows in the cold, and the second number tells you how stable it is when things get hot. Picking the right one is literally the difference between a V8 running smoothly for decades or completely tearing itself apart.
So we've pulled apart the mechanics, the history, the sound, and the lifeblood of this incredible machine. But all of this leaves us with a pretty provocative thought. Today, engines are shrinking, turbochargers are absolutely everywhere, and maximum fuel efficiency is the ultimate goal of the industry. Let's be honest, the V8 is large, it's thirsty, and it's complex. Yet, as we've explored today, its glassy smoothness, its instant power delivery, and that deep, soul-stirring rumble are completely unique to its specific mechanical geometry. With the automotive landscapes shifting so dramatically beneath our feet right now, will the raw, mechanical passion for the classic V8 actually endure into the next generation? I'll leave you to ponder that one. Thanks for hanging out with me on this explainer, and keep learning.